first energy form we want to look at is kinetic energy. So if I were to ask any of you what kinetic energy is, you would tell me 1/2 mv squared. So I know that's the case. Ke equals 1/2 mv squared. In the text, it goes through how this is developed from a work expression, but here I figured you can read the text. We'll go through here. So if I look at this, the units here are kilograms, meters squared over seconds squared. So I have a kilogram meter, so I have a Newton meter or joule. So if I look at this, this is a Newton meter or joule, so that's what we have. And if I want kilojoules, so the units on this are joules. So if I do Ke is equal to 1/2 mv squared over 2,000, I have, that's a terrible B, I have kilojoules. So very often we're dealing with kilojoules, so it's mv squared over 2,000. And so now let's look and see what this looks like with an example. So you know this. So we have a car that's moving at 60 kilometers per hour. It's a 1,000 kilogram car, and I want to find the kinetic energy. So we have a 1,000 kilogram car at 60 kilometers per hour, and I want to find Ke. So I'm going to draw a sketch. So I have the car, it's going 60 kilometers per hour, weighs 1,000 kilograms, and I want the kinetic energy. So in this case, we're going to evaluate these terms. And so what we need to do is pay attention to here, the velocity was in meters per second squared. Or meters per second, if I square it's meters squared per second squared. So what I need to do now, this is in kilometers per hour, so I need to change this to meters per second. Now you can look it up and Google it and do the conversion factor, but we can also just figure it out. So the velocity is 60 kilometers per hour times 1 over 3,600 seconds per hour times 1,000 meters per kilometer. So I can do that, and you'll see the units cancel here, here, wherever I am. And so I have meters per second, and so I have the velocity is equal to 16.67 meters per second. And I can solve for the kinetic energy. So the kinetic energy, 1/2 times 1,000 times 16.67 squared. And this is going to be 13 followed by 48. joules. Well, that's a ridiculously big number to work with, so let's divide by 1,000. And so if I do Ke over 1,000, I have 138.8 kilojoules. And so it's the same number, but it's a more manageable figure in this case. And now we want to look at another energy form that a system has, a closed system. So far we've dealt with velocity. So I have its velocity. I could also drop this thing. So I could drop it, and I could have a change of its gravitational potential energy and make a mess with chalk on the table. And so in any case, let's do that, and we'll look at gravitational potential energy. And so, in this case, I'm going to have a mass. It's above the Earth's surface, a distance z, and I have gravity g. And so the potential energy, PE, is equal to mgz. And so this is kilograms, meters per second squared, meters. And with that, we end up with joules. And if I want kilojoules, I have to divide by 1,000. So if I have PE over 1,000, mgz over 1,000 kilojoules. And so what happens is very often we are using equations where we're using kilojoules, and that's what we want to do. So let's look at the change of potential energy if I dropped a 20 kilogram bag of sand 100 meters. So let's say I was up in a hot air balloon. Oops, there goes the bag of sand. Boom, I hope no one's below. So let's be up here, so we have 20 kilograms. It's going to drop, I have 100 meters. And I want to find the change of potential energy. So it's going to drop. And so I have PE2 minus PE1 is mg Z2 minus Z1. And so here is Z1. And obviously Z2 is on the ground, so it's 0. So what we have then is this is 20 times 9.8 times 0 minus 100. And this is going to be minus 19,600 kilojoules, or minus 19.6 kilojoules. And it's a decrease of potential energy because I had the mass, it had potential energy, a greater potential energy, it went down to the ground, and now it has less potential energy. Normally, if Z is this datum is 0, then that's as low as you can go. And so these are two of the energy forms that we have. So I now have this, my eraser. So I have the eraser, it can be moving, it can be up in the air, so it has kinetic energy, potential energy. What about the energy associated with the substance itself? So everything else we call internal energy. So we make this lump sum, everything else is called internal energy. So U is this is the energy associated with substance's structure. So for instance, water at 50 degrees C and 1 atmosphere, large U over M is little u, or is equal to 209.55 kilojoules per kilogram. So this is the specific internal energy. And so there, in chapter 4, we'll get in terms of how we evaluate this for water and other pure substances, but right now we have that. And so from a qualitative perspective, I can look at how energy is stored within a molecule, and let's see, I have to put down a piece of paper to do that. So what we have is I want to look at, and this now looks qualitatively at the microscopic level. Microscopic view of energy storage. in a molecule, in a diatomic. So I'm going to have this diatomic molecule, and I can have energy storage manifest. So here it is. Here's my diatomic molecule. It's a handy piece of chalk. And so what it is it can have velocity associated with it. It can have velocity in the XYZ direction. So it can go up and down, back and forth, in and out. And so that's 3, right? And so with that, so translational kinetic energy at the microscopic level is manifested as temperature at the macroscopic level. But I could also have other modes of energy storage. I could have these things vibrate. So they could go boop, 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 boop. And so they could vibrate and store energy too. So I could put energy in, and it wouldn't make it go faster, it'd make it vibrate more. I could have it also rotate. So it could rotate, each one could rotate, spin faster. So I could have each one rotate, and I could have the whole thing rotate. So at different temperatures, molecules will store energy differently. And so we don't really need to know that in the macroscopic perspective, but we can just gain a qualitative understanding of it from a microscopic perspective.